right, here we are back, and I did have one question at the end of class that I guess I wasn't quite clear about what the question is, and I said, oh, let me go visit this tomorrow. So who asked that question? It was somebody over here. Did you study it later and get your answer questioned or question answered?
Honestly, I couldn't really figure it out.
Okay, so let's take a look at that. So the one thing that you didn't understand, if I remember correctly, was going from this step to the next step. Would you agree? Yes? So if we look at the properties here, there's one here, and it's going to be A plus BC is equal to AB. Oh, and this is, I believe, missing a plus in here. And I think that might be the confusion. All right, that there's a plus in there that is missing, and that's why. Let me see if it's in the book correctly. Oh, I'm sorry. It is A plus B A plus C. So A plus B, A plus C is, oh, there it is right there. That is correctly. Yeah, this is the one that was incorrect. It needed the plus right there and the plus right there. And so if we look at what happened here is, remember we said A plus BC, right? Well, in this case, this is A, this is B, and this is C, because all we're doing is we're replacing with whatever it is. So in the replacement, that's A, that's B, and that's C. So obviously, there it is. P went down to P, H prime went down to H prime, and then A was duplicated there and there. Okay, so you got that step? Okay. I think your confusion might have been maybe that previous slide had a typo in it. And I will probably, I will go out there and fix it and upload it correctly. And I see a couple of you actually have printed it out, so you could do that. And then there's your simplified circuit. Now, interesting, notice this, because we went through the Boolean algebra and the properties associated with Boolean algebra of simplification, we went from a design that was 5 gates to a design that was 3 gates. And that's the whole reason why it's nice to do the algebraic simplification, so that you don't have all this extra hardware there associated with the design. So let's go on. Again, looking at our commutative properties over here, we are going to see if we can identify our door opener. Remember, we looked at this. So let's apply the Boolean algebra. So rather than me talk about this, I would like for you to go through these properties right here, do it with your neighbor, see if you can go through all the different steps, and does it minimize down to this? All right, let's look at the Boolean algebra process. Ooh, what happened here? Oh, I went to end. Not very good. I wonder how far back I gotta go. Oh man, I gotta go way far back. Yeah, this darn end key is right next to the page down key. How close am I? Right here, right? So that is our Boolean algebra or equation, right? So based on the distributive property, which one? Well, we're looking at this one right here, or this one right here.
First one.
So we're looking at C prime H. C prime H is the same thing between the two, right? And so in that, and then there's a B and a C over here. So that would be, in this case, oh yeah, A is what is the C prime H, because it appears in both sides. So we're doing this way to the distributed property. And from this we pull out P plus P prime. And P plus P prime is 1. So then we can minimize that from this step to this step. All right, so what else do we see? Oh, we took it away from the identity process, which was anything and 1 is anything. So anything and 1 is anything. And commutative, we're just moving stuff around inside. And it's the same. Ding, 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 ding. Yay, we're done. So we only used what? Really, only one was relatively tricky, right? Everything else, this was pretty easy. The complement. There are some other additional properties. Null elements. So A and 0 is 0, A or 1 is always 1. Did we have that earlier? No, we didn't. Idempotent. A plus A is A. I should say A or A is A, and A is A. Involution, A prime, prime. So you're taking a negative, so a not of a not, right? We've seen that a little bit earlier. De Morgan's law, oh, you've probably seen something like this before, right? Or is that in 2111? A or B complement is actually A complement and B complement. This is very useful, as well as this, meaning A and B complement is the same as A complement or B complement. These are probably one of the more useful ones you'll see later on. So, in fact, let's take a look at an example of De Morgan's law. So, I like this. Aircraft lavatory sign example. So you've seen that sign in the front of planes, right? So you have 3 lavatories, each with a sensor A, B, and C. And it will be 1 if the door is locked. So if the person is actually in there and they didn't lock the door, first of all, you embarrass them, and it serves them right. But if it's all locked. And the whole idea is you want the light to say available. So it'll be green if any lavatory is available. And the assumption that these are all grouped lavatories in the same area, because some planes have them in the front and back. All right. So your equation is if A is not locked and B is not locked and C is not locked, I should say. If A is not locked or B is not locked or C is not locked, then you could say that it's available. And since this is by De Morgan's law, as we saw up here, if we're having the complement and we're all ORing them together, it's the same as ANDing them and then taking the complement. And what's the difference? Well, 1, 2, 3, 4 gates versus 1, 2. So you have a bit of a savings there. And another example for that door opening example that we had earlier. What was C? The door is force closed. In other words, you don't want it to be opened. So prove that the door stays closed, F is equal to 0, when C is equal to 1. In other words, we set that door don't open the door. And based on the formula, as you can see, if we have our formula C prime and H or P, H I believe is somebody present, right? And P is we allow it to be opened. Or there's a switch there that says just stay open, right? So as long as C is equal to 1, take the complement of a 0, we're going to be ANDing 0 with anything, and remember 0 ANDing anything is 0. We could also have a complement of a function, meaning that if you take f prime over here, if you have f and you want to know what f prime is, then simply all you need to do is contain that in a parenthesis and add the prime as well. And then going through De Morgan's law and De Morgan's law again, you could expand it into a sum of products. And so we're going to look at this in a little bit of detail. By the way, it could also be a product of sums. So we're going to look at a couple more examples later, so hold off on your thoughts if you have it. So let's take a look at Boolean functions f. In fact, you want to do that now? You want to do some examples now? Some examples of De Morgan's laws? Let's go do that. So let me think of a good one to come up with. So here we have some functions, and or a function, and just for grins, I'll write it up on the board because then I'm going to put the properties up there that we could look at later. So we said f is equal to ABC not plus ABC plus A naught BC plus A, B naught, C. You know, just for fun, I would like you to do the following two things. Number one, show me the truth table. And then number two, see if you can simplify with Boolean algebra. All right, you got that done? You got that question?
So you want us to make a truth table first, then simplify, then another truth table?
Nah, just do the truth table, and you know, with F, don't forget, you might have to do some intermediate things. Or do you have to do the intermediate things? Well, based on the this right here, which is a sum of products, right? This is going to be, first of all, how many lines will this truth table have?
8.
All right, it'll have 8. And this right here represents how many lines of that truth table? Just this right here represents how many lines? Just one. So you have to find out what line this is. What line is this? What line is this? And you know what? I'll make life a little bit easier. So that makes it a little bit more reasonable. So go ahead and do that one. Here we are, and there is a trick that I want you to realize. Remember, there was a specific identity that said A is equal to A or A. So one thing that you could do to make this really easy is to duplicate something. And so I'm going to duplicate ABC. All right? So now we're left with this. And in this case, I have BC here and BC here with an A and an A prime there. So which property is this? Distributed, right? So the important thing to note is that I'm going to draw this with a different color. I added that over here with the property A is equal to A plus A. Which identity was that again? Or which, well, let's look back over here. Is one of those new properties I pointed out. That is the idempotent. That just almost sounds too wrong. All right, going back to our example here, and then we went from this step to this step, and that was distributed, right? Let's go back. Aren't I showing this right? Where'd it go? This one right here? And of course, A and A prime, or A or A prime is what? 1. And then the 1 added with anything else is 1. So we're left with this. Now take a look at this. We have A and C here. So then we could pull out A and C. B or B prime, again, this is distributed. And so now we're left with this and this and this. So is that our simplification? Yeah, it kind of looks like that. So if you have the function over here, we have a a 1, a 1, a 1, and a 1. So we started with 4, and I added this ABC, which was kind of like another one over here. But there's a reason for that. So I could use the algebra to put that in place. Now, it is not in here. I got to make sure he didn't add it in the last version. I didn't check. Wow, he doesn't even do that until all the way in the end. So I'm going to just do it anyhow. There's a neat way to optimize this, and that is by using something called Karnaugh maps. And Karnaugh maps is actually covered in chapter 6, and I'm going to refer to that soon, and I'm just going to give you a taste for this, all right? And so the taste is as follows. I had my sum of products, and I could create a visual way to group things. And so here's my visual way to group things. If I have, let's see, A is equal to 0 here, and A is equal to 1 here, and A is equal to 0 represents that row, equal to 1 is represented this row. And on these columns here, this will be B and C. And when B is 0 and C is 0, this is my result. So let's see, when A is equal to 0, B is 0, and C is 0, that line, I have that. So this is element number 0. When A is 0, B and C, this is element number 1. This is element number 2. This is element number 3. So if we're doing it 0, 1, 2, 3, 4, 5, 6, 7, notice that we kind of group these so that going from one of these columns to the next column is changing 1 bit. So in this case, we're changing the C bits going from 0 to 1. B stays the same. At this point, we're changing the B bit. At this point, we're keeping the C bit there. And then in this column, we're changing the C bit. Oops. So this truth table is just represented by this K map here. Not to be confused with a K cup. You're supposed to laugh at my jokes. Nobody wants an A in this class, do they? All right. And so to minimize, I know I could visually look at my K map, and if I could group these ones together, I could actually minimize my equation. And it turns out that I could group these two together, and I could actually group these two together. And so that way, and by the way, this can't be grouped with, I can't group with this one here, I can't group with this one there. I could even go and try and group over there, or try and, well, that's it. I can only try and group this with this one over there. And so this one's going to stand alone. So according to my K-map, I'm going to have one of my elements in the equation that will have 3 variables. This circle will have 2, and this one will have 2. So let's see what I got. Oh, I got one that has 3 and 2 and 2. So in the process of this, in the Boolean algebra, I knew that by using the idempotent, if I got that right, by adding in another of these A, B, C's, remember A is equal to A or A, then I could combine these two here and simplify my equation. Now, was that cheating? What do you think? It's another tool that you have. Now, as I mentioned, K-maps is over here in the chapter that says optimization and trade-off. And so we're actually going to go off to that chapter and have you look at some of that and I'm going to do that for the next class because we're almost done with this class. So for the next class, I would like you to go ahead and read chapter 6. Specifically, I want you to read chapter 6 through page 342. So I'm going to have you literally read, how many pages is this? 25 through 42. So make sure you read that for the next class. I'm not done yet though. Returning back to the slides. So we're looking at these general logic equations and Boolean functions and what's going on with the real world. So you could have English statements, right? You could represent it with a function using Boolean algebra. You could do equations, you could do circuits, you could do truth tables. These are all different things in our toolbox. So there's an example of the equation for number 1, and there's an equation for number 2, and you could do the circuit. There's one for number 1, and there's another one for number 2. So there's a whole bunch of things that you can use in your toolbox. Truth table will also show that up. Now, actually, if you were to look at this in the truth table, what one thing jumps out to you? Well, the first thing that should jump out is that it doesn't matter what B is, right? F always follows whatever A is, and you could see that from the truth table. And literally, if you look at this, are these two the same? Yeah. So based on some of our identities, or our Boolean algebra properties, we can see what? Oh, here is A prime. This turns out to be A prime. And this will be B or B prime, right? This is from the distributed property. And of course, this simplifies down to 1. So these two functions are the same. Somebody raise their hand? Yes?
Can you see it on the diagram based on, since B is going through a negating gate, and then it goes through the normal AND gate, you can tell that B is going to be.
Actually, eyeballing this is really tough to see if you could simplify it that way, right? This might be a little bit easier, but then again, this only has 2 inputs, right? So what's the way you really know how to do that? Well, it really comes down to Boolean algebra is one of the best ways to identify how to simplify. But the other option I'm going to give you is going to be K-maps, and which we'll look at later. And in fact, if we were to look at this for a K-map, you would say, based on B up here and A down here, it is a 4-entry. So when B is 0 or B is 1, A is 0, A is 1. So let's look at this. When A is 0, you have 1 and B is 0. When A is 0 and B is 1, you have 1. And then right here you have 0 and 0. Would you agree with that? And one of the examples I showed you earlier with respect to the K-maps is, if you have 2 of them that are right next to each other, you can group that together. And then by that grouping, you notice that it doesn't matter what B is. A, when it's A prime, that's when our function is going to be 1. And I think I've gone over the truth table representation of Boolean functions. I've kind of, beat this into you a little bit earlier. I'm sorry. I showed examples of this earlier, right? I shouldn't be beating you at all. So just for fun, let's spend a couple of minutes. Oh, we don't have a function yet. Function is 1 when A, B, and C is 5 or greater in binary. So for this table, when A, B, and C is 5 or greater, 5 decimal or greater in binary. So when would that be? The last 3, right? And the rest of these are 0. Looks good. Oh, what do you know? Same thing. And we'll put zeros there. And just for fun, let me do one more. Let me do the K-map. So in the K-map, when A is equal to 0 and A is equal to 1, and when B and C are 0, 0, 0, 1, 1, 0, or 1, 1. Well, first of all, whenever A is 0, it's always going to be 0 here, right? And when A is 1 and B and C are 0, that's going to be 0. And then the other times it's going to be 1. So if we look at this from a K-map respect, oops, I'm supposed to do that. We can group those two together, but we could also group these two together. So our end function is going to be whenever it is A and, oops, I'm sorry, this is supposed to be 1, 1, and that's 1, 0. So here's 1, 1, and then that's 1, 0. So whenever what? Looks like whenever C is 1. So then we can change, or we can say that this is going to be whenever AC, or again, it's whenever A is equal to 1, and we look at these two. Oh, B is 1. B is 1. And we're just able to tell that from the K-map. Looks like fun. Let's visit it next time we meet next week.